Hi everybody. This is going to be our first video on Chapter 8, which is going to be linear differential equations of order n. So we are no longer dealing with just first order equations, okay? We're going to be dealing with equations of any order. So starting with section 8.1, this is going to be a long video because it's laying down the groundwork for the chapter. So this is going to be general theory for linear differential equations. Okay. So we're going to start off with a definition. So we're going to let D be a map that goes from C1 of I to C0 of I, given by D of F is equal to F prime. So D is just a map that takes a function to its derivative. Remember, C1 is just functions that are differentiable, right? We need a function to be differentiable to be able to take a derivative. So this guy D has a name. D is called the differential operator. Differential operator. Okay? So with this differential operator, we can define derivatives of all orders. So we can define higher order derivative operators as follows. So D squared is just going to be D of D, right? In other words, we're taking the derivative and then the derivative again. D cubed is going to be D of D squared, right? So in other words, it's three derivatives. We could keep doing this, right? We could just keep doing this all day. So what would D to the K be? D to the power of K would be D of D to the K minus 1. So what this means is that we can now define any order derivative using this D operator. So this means that D to the K, since we're taking K derivatives, we need it to be K times differentiable. And so this maps to C0 of I, right? So this map is given by D to the K of a function F is equal to the kth derivative of X. Let me back that up, right? Kth derivative. Okay. Now, what is special about this D map, right? In this case, we have a D to the K map. Since D to the K of F plus G is equal to the kth derivative of F plus G, recall, oh, sorry, I shouldn't say, sorry, I wrote that wrong. Since this is equal to, think about it, when you take K derivatives of the sum of two functions, we know from calculus that this is going to equal the kth derivative of F plus the kth derivative of G, right? So we know that this is true, which is the same as D to the K of F plus D to the K of G. Also, what would D to the K of C times F be? this is just equal to c times d to the k of f, right? Because this is all stuff we know from calculus, that when you take the derivative of a constant times a function, the constant pulls out, right? And that's true even for k derivatives. So what does this mean? This means that these are the two properties of linear transformations, aren't they? So this means that every single d to any power you want are all linear transformations from c to the n of I to c to the 0 of I. So since they're all linear transformations, it's also true that any linear combination of them is also a linear transformation. And so this leads us to the following important definition that we're going to be using for the rest of the chapter, okay? So, definition. We have something called the general linear differential operator. Of order n. So general linear differential operator of order n. What is that going to be? This is when you take a linear combination of all of the di's, right? So this is what it looks like, where each ai is a function of x. Okay, so in other words, we could take all of these operators and create a linear combination of them with functions, and this is how we get our general linear operator, which we call L. And what do we notice about L? L itself is a map, right? It takes Cni to C0 of I. This guy is a linear transformation. And how is it defined? Well, if you apply it to y, what you end up with is, so the way that you apply that map up there to a y is you just take that many derivatives and you multiply as necessary. So it's going to be the nth derivative of y plus a1 times the n minus first derivative of y plus a2 times the n minus second derivative of y. Keep doing this. And this would be just y prime. And then we have an times y itself. Okay, so in other words, we can build a brand new function by applying this linear operator to it. Okay, it takes a function to another function. Let's do an example so we can understand how to apply these linear operators to functions, okay? And we're going to do it for a particular function. So example. Let's let L be the following linear operator. Find the following. So part A, what would L of y be? Part B, what would L of sine x be? Part C, what would L of x squared be? So let's first do L of y. Since y is just a general function, we're going to apply that map up there to y. And what do we get? We get y double prime plus 4x times y prime minus 3xy. Okay, so this is what it means to apply that operator to any function. So how would we apply it to sine of x? This is a particular function now, right? So what would the second derivative of sine x be? Well, first derivative is cosine, and then we get negative sine x. So we get negative sine x plus 4x times cosine x minus 3x sine x. Okay, so there you go. What would you get if you apply it to x squared? Well, second derivative of x squared is, let's see, first derivative is 2x, second derivative is 2. So you get 2 plus 4x times, what's the first derivative? 2x. And then minus 3x times x squared. So what do we get here? We end up with 2 plus 8x squared minus 3x cubed. Okay, so this is an example of how we can apply one single linear operator to three different things, right? And this is what it means to apply a linear operator. It's just a map that is taking a function to another function. Let's do another example, okay? This will be an interesting example because the linear map is a transformation. We could ask what the kernel of that transformation is, right? So let's let L be the map D minus 2x. Find the kernel of L. So what would the kernel of L be? It's the set of all functions such that L of y is equal to 0, right? What is that equal to? Well, it's the set of all y such that, what's L of y? Well, we're taking a derivative, and then minus 2xy is equal to 0. Okay? So in other words, we want y prime minus 2xy to equal 0, so we need to go ahead and solve that, right? But what does that mean? That means that dy dx is equal to 2xy. And this is a separable differential equation, so can't I write it this way? dy over y is equal to 2x dx. Now you'll notice that I just divided by y, so I made an assumption that y was not 0, so we need to remember that. So if I now integrate both of these, I end up with the natural log of the absolute value of y is equal to x squared plus c. Okay? So what do we end up with here? This means that the absolute value of y is equal to e to the c times e to the x squared, which means that the absolute value of y is equal to, I can call that d e to the x squared, where d is any non-zero number, so d is not 0. So this means that y is equal to plus or minus d e to the x squared, where d is not 0. But here's the thing, if you look at the original differential equation right here, right, you notice that y equals 0 does solve if we call this star, solves star also. And so we could just throw in the d equals 0 case, because y equals 0, you get that by just setting this d right here equal to 0. And so what does this mean? This means that the kernel of L is exactly the set of all functions that look like what? That look like, let me call it d1. How about d1 e to the x squared, such that d1 is a real number, right? Because that gives us every possible answer there. So this would be the kernel. Right? The kernel is a set of functions, and those are the set of functions that get mapped to 0 by that linear operator. Okay? Let's go back to talking about differential equations, right? We have not talked about nth order linear differential equations except for giving a definition previously. So let's go ahead and write this as a definition. So let's consider the general nth order linear differential equation. It's a naught of x times nth derivative of n plus a1 of x times n minus first derivative plus that. This time I wrote them as clear functions, right? And this, we could call this, and then I'll call the function on the other side as f of x. This is what an nth order linear differential equation looks like. Okay? So recall, I want you guys to recall some terminology here. If the function on the right, so if the function on the right is identically 0. By the way, those 3 equal signs just reminds you, I don't mean if it equals 0 at certain x's, but is identically 0. So let me write this notation here. This means is identically. Okay, so if that guy is identically 0, we call the above differential equation homogeneous. Otherwise, it is called non-homogeneous. Okay. Homogeneous and non-homogeneous differential equations are going to be dealt with in different ways. The non-homogeneous case is going to involve more work to solve, definitely. But the homogeneous case is what we will deal with first, okay? So, as usual, you can put this thing in standard form, and that's what we usually like to do. So let me just say dividing. You can always divide by this first term right here in order to turn it into standard form, right? So dividing by a naught of x puts the differential equation in standard form. So what's standard form going to look like? It's going to look like this. Nth derivative of y plus a1 of x, nth derivative of y, or sorry, n minus first derivative plus y prime plus a n of x times y is equal to f of x. So you'll notice, by the way, that these these AIs are not the same as the AIs above, right? What we're doing is we're creating new functions by dividing by that first one, okay? So this is important. So let me just say each AI of x is different from AI of x in star, okay? So these are different functions, okay? So this is called standard form, okay? I'm going to call this star, okay? This is what I'm going to call star, and this is what I'm going to be referring to as I move on. Super important here, my standard form differential equation. This is what an nth order linear differential equation looks like. Okay? So we can write star as follows. Now here's the nice thing. We can write it in very compact form. We can write it as Ly is equal to f of x, where L is that differential operator that we wrote down before. Okay, so this is another way of writing it. I'm going to go ahead and call this, if I need it again, I'm going to call it star star, okay? So star refers to the differential equation up here that I boxed, right? But this other guy that I'm boxing is just another way of writing the same differential equation. Just understand that the L, the linear operator, stands for all of that. That's what tells you what to do to y. Okay, so these are just two ways of writing it. Now, I do want to talk a little bit about initial value problems. It turns out that a solution always exists and is unique. So this is called the existence and uniqueness theorem. We need to talk about this because this sort of forms the foundation for initial value problems. So this is called existence and uniqueness. Okay, so let's let A1, A2 to AN and F all be continuous functions on some interval I, then for any x naught in I, the following IVP. I'm going to write the IVP right now, okay? There's our IVP, and I need to write down a lot of initial conditions. So y of x naught is equal to y naught, y prime of x1 is equal to y1. All I need is n initial conditions, and I need one per derivative. So, oh, sorry, these do, 1 second. I wrote this term up here down. This should be an x naught. These should all be x naught that I'm plugging in. Same initial x value, even though the y values, of course, are different, okay? So this IVP that I just wrote down, the theorem says that this IVP has a unique solution. On the interval I. Okay, so this is our existence and uniqueness theorem, right? We're not going to be proving this theorem, but this is an important fact that we're going to be using. Okay? All right. So let's now start talking about homogeneous linear differential equations in particular. Okay. Consider any nth order linear differential equation, okay, which we called star before, and we're going to define L as in star star, okay? So just to remind you of what those are, L corresponds to what I wrote down in the second box. So let's suppose that Ly is equal to f of x is our differential equation, right? That's a general differential equation. Okay? Let's let S be the solution set to Ly equals 0. We've seen this before, right? The set of all linear operators that send y to 0, the set of all y's that get mapped to 0, right? Let's write that down as a set. Remember, we're talking about the solution set, so it's a set of all y's such that Ly is equal to 0, okay? That's just equal to the kernel of L, and we know that the kernel of any transformation is a vector space. Okay? This is extremely important. It is a vector space. The reason that this is in Chapter 8 is because we can now use vector space theory on this. Of course, we are worried because what if this vector space is infinite dimensional? Then we can't use all this stuff that we learned about finite dimension. However, we have an extremely nice theorem. The theorem says the following. The solution space to the nth order homogeneous linear differential equation Ly equals 0 is a vector space of order n. Or sorry, not order n, dimension n. Sorry, I wrote that wrong. Dimension n. Okay. Super important theorem. Super important theorem. So here's what we're saying, okay? What we're saying is that the solutions to the nth order homogeneous linear differential equation, which looks like Ly equals 0, must have dimension n. In other words, there must exist n linearly independent functions that form a basis for the solution space. So all solutions are made up of those. So now we can use some vector space theory that we know. So what does this theorem imply? This theorem implies that if y1 of x to yn of x are n linearly independent solutions to the differential equation Ly equals 0, they must form a basis, because remember, if you have n linearly independent things in an n-dimensional vector space, then they must also span, right? So they form a basis. They must form a basis and thus any solution to the differential equation Ly equals 0 must be a linear combination of those functions. This is a big deal. So another way to restate this, okay? Another way to restate this is if y is a solution to Ly equals 0, then since it's a linear combination, that means there exists scalars C1 to Cn such that y must be a linear combination of those functions above. This is exactly what we just wrote down here. This is called the general solution to the linear homogeneous differential equation. So, of course, this leads us to the following question, right? Okay, we know that we have n linearly independent functions then that we can use to build all of them, but of course the natural question is, how can we tell if a set of solutions to a homogeneous linear differential equation, how can we tell if they're linearly dependent or linearly independent? So this brings us to the return of our old friend, the Wronskian. So this is a theorem. And the name of this theorem is called the Wronskian test. It says, let S, which is these n functions, let this be a set of solutions to the nth order homogeneous differential equation Ly equals 0 on an interval I. And we're going to let W of all of these guys denote their Wronskian. So this theorem has two parts. First, if the Wronskian Sorry, my notation's not very good here. This should have been brackets here, just because Wronskian are usually written with brackets, okay? Remember, I'm being a little sloppy with my notation because these should be of x, right? These are functions. It is a function of x, the Wronskian, right? But you know, if you don't write the of x, it's fine as long as you understand that it is a function, right? So if this guy, the Wronskian, at a point x naught is equal to 0 anywhere, or let me just say this, for any x naught in I, then S is linearly dependent. Okay? The other thing the theorem says, of course, is if, this is actually a very powerful theorem, if the Wronskian of x naught is not 0 for any x naught in I, then S is linearly independent. Okay, so super important theorem. This is saying that the Wronskian has to be 0 anywhere, then it's linearly independent. And if the Wronskian's not 0 anywhere, then it's, if the Wronskian is 0 anywhere, then that means it's linearly dependent. And if the Wronskian's not 0 anywhere, then that means it's linearly independent. Now, of course, we do mean that it's linearly dependent on I, right? On the interval that we care about. But of course, everything is with respect to the interval that we care about. Super powerful theorem. And by the way, what this implies is that you can't have the Wronskian be 0 sometimes and not 0 other times. It's either going to be 0 everywhere or non-zero everywhere. That's what this theorem implies as well. So let's do an example. So this example find all solutions to the differential equation y double prime minus 2y prime minus 15y equals 0 of the form y of x is equal to e to the rx, where r is a constant. And then this is part A, and part B is going to be use this to determine the general solution. It's not even clear how we can use part A to find part B, right? But the idea here is that maybe part A, solutions that look like that are basically comprise all of them. And that's what we're going to see, okay? So let's start off with this function. What I'm going to do is take this guy and I'm going to plug it into here, and so that I could see what the solution would be forced to be. So we're doing part A here. So let's suppose that y of x is equal to e to the rx. What would y prime of x be? Well, we're taking a derivative, so it's r e to the rx. And what's y double prime equal to? It would be r squared e to the rx, right? Just because taking derivatives is quite simple when it comes to these guys, right? So if we plug it into the differential equation, we get the following. R squared e to the rx minus 2 times y prime, so r e to the rx, minus 15y, so minus 15 e to the rx is equal to 0. What does this mean? Well, I can actually divide the whole thing by e to the rx because e to the rx is never 0, right? E to the nothing. There's no way to raise e to the power of anything to get 0. So this means that we get r squared minus 2r minus 15 is equal to 0. And so it boils down to solving this quadratic. So we know that that factors into r minus 5, r plus 3. That's equal to 0. And so what that means is that r is negative 3 and r is positive 5. So this means that y of x is equal to e to the negative 3x, and y of x is equal to e to the 5x are the only solutions of the form e to the rx. Okay, so those are the only values for r that work. Now, part B asks us a stronger question. Part B asks us to find the general solution. But how would we do that? Well, we actually need to check if those two solutions that we found are linearly independent. So let's go ahead and find the Wronskian, okay? So here's what I'm going to write down, okay? So we're going to write y1, let's call y1 of x equal to e to the 5x, and y2 of x is equal to e to the negative 3x, okay? So what would the Wronskian of y1 and y2 be? Remember, the Wronskian is the determinant of, you put both functions here, and then you take their derivatives, and we only need to do one derivative in this problem because there are only two functions. We're going to do the determinant of that 2 by 2 matrix. So what is this equal to? This gives us negative 3. We're doing diagonals multiplied, right? Negative 3 e to the 2x, right? Because 5x minus 3x is 2x, minus 5 e to the 2x, which is minus 8 e to the 2x. And of course, this is not 0 anywhere or everywhere, depending on how you want to word it. So what does this mean? This means that the functions y1 and y2 are linearly independent. Okay? But now remember, we were dealing with a second order, weren't we? Since y double prime minus 2y prime minus 15y equals 0 is a second order homogeneous linear differential equation, the solution space has dimension 2. So what does this mean? This means that our two functions that we wrote down forms a basis. For the solution space. In other words, every single solution must be a linear combination, and so this implies that the general solution to the differential equation is, just write down a general linear combination of those two functions. So I'm going to write c1 e to the 5x plus c2 e to the negative 3x. So in other words, every single solution must be a linear combination of those two functions because they form a basis. Okay? This idea of e to the something, when does this pop up? We're going to find out very soon once we get further into this chapter. What we did here is no coincidence, okay? It turns out that these are going to be the solutions to a differential equation that looks like this. And we'll go a little bit more into why, or what special form that takes on in the next section, okay? So, we're not done with this section, though, because we just talked about homogeneous linear differential equations. So now let's talk about non-homogeneous linear differential equations. Now, what does it mean to be non-homogeneous? It means that, of course, we do not have a zero on the right side anymore. We have a function, right? Now, unfortunately, this does not form a vector space. This is the bummer, right? We are not, this doesn't form a vector space. However, you can see that you're about to see that we're about to use a trick, okay? So, definition. What we can do is create an associated homogeneous equation. So I'll just say for the above differential equation, its associated homogeneous equation is, so it would be the same one sorry, that was sloppy. So, do you guys see the difference? The only difference is that I replaced the capital F of x with 0. This is called the associated homogeneous equation. Okay? So, what this means is that if we have Ly equals F, then Ly equals 0 would be the associated homogeneous equation. Okay, so of course the big question is, how are these related, right? How are these related? Okay, so let's do a theorem, or talk about a theorem, which should clarify how these two are related. So suppose y1 to yn is a linearly independent set of solutions to, now remember, let's just look one more time. I'm calling star the non-homogeneous, and I'm calling double star the homogeneous, okay? So question, how are these related? So suppose we have a linearly independent set of solutions to double star, the homogeneous, right? So suppose we have that, and let YP be any particular solution to the non-homogeneous. Okay, so what we're saying is if you have all solutions to the homogeneous and you have any solution to the non-homogeneous, then every solution to the non-homogeneous is of the form we already know that linear combinations make up all of the homogeneous solutions, but all we need to do is add in that particular solution, and this gives us all solutions to the non-homogeneous, where C1 to Cn are scalars, of course, right? So these are scalars. Okay? So a good question, of course, is why? Why does this work? So I'm not going to give a proof, but I sort of want to give an outline of why this works. Okay? Let's give an outline of why this works. So suppose that YP solves Ly is equal to F. So in other words, what that means is L times, or L applied to YP gives you F, right? That's what that means. Okay? And suppose, so I guess actually this is a proof, okay? Suppose that U is any, let me write this as U of X to remind you that this is a function. Suppose U of X is any solution to Ly is equal to F. So what does this mean? This implies that Lu is equal to F and L applied to YP is equal to F. So what this means is that Lu is equal to L applied to YP, which means that Lu minus LYP is equal to 0. But we know that this is a linear transformation, so I can write it this way. U minus YP is equal to 0. But wait a minute, now that means that this guy, so this implies that this guy inside of here solves the homogeneous, doesn't it? Because L applied to it is equal to 0. So this implies that there exists C1 to Cn in R such that U minus YP is equal to C1y1 plus C2y2 plus Cn.yn, and so this implies that U is equal to C1y1 plus Cn.yn plus Yp. And there you go. That's exactly what we were trying to prove, right? That every solution looks like that. So here's the thing, guys. We're going to invent a new notation here. So this guy right here, we have a name for that. That's called YC. Okay, YC. What does YC stand for? YC is called, we call that the complementary function. Oh, sorry, I wrote that wrong, or I spelled it wrong. Complementary is with, oops. Complementary, okay. So YC is called the complementary function of Ly equals F. Okay, Ly equal F. And so if we call that YC, then here's what we end up with, okay? The theorem states, so this implies that the general solution to Ly equals F is you just take the complementary. This is the solution to the homogeneous, and then you take any particular solution and you add them together. Or another way to write it is just in shorthand, YC plus YP, okay? So this is how you build the general solution to a non-homogeneous, is you find all the solutions of the homogeneous, and then you find any solution, any particular solution of the non-homogeneous, and then you add those together, and that gives you the general solution to the non-homogeneous. Okay, super important fact. Of course, finding this particular solution is not easy, so we're going to be devoting this whole chapter to this. Okay, let's do a quick example now where we apply this in practice. So, example. Verify that yp of x is equal to 2e to the 6x. We're going to verify that this is a particular solution to the non-homogeneous equation y double prime minus 2y prime minus 15y is equal to 18e to the 6x. Okay, so that's part A, and part B will be to find the general, let me call this star, find the general solution to star. Okay, so we need to verify that that guy is a solution, right? So let's go ahead and check it. So what is yp prime, first of all? Take its derivative, you get 12e to the 6x. And what's yp double prime? Multiply that by 6 again, we get 72e to the 6x, right? And so let's plug it in. We end up with 72e to the 6x minus 2y prime, so I'm just going to multiply it by 2. I get 24e to the 6x minus 15 times y, but y has 2 in there, so minus 30e to the 6x. And then the other side has to be 18e to the 6x. So is that true? Well, 72 minus 24 minus 30 is indeed equal to 18, right? So 18e to the 6x equals 18e to the 6x. This is true. Okay? So we found a particular solution. Well, we didn't find it. The problem gave it to us, right? So in other words, what we showed is that this guy is a particular solution. Now, that was all part A, but how can we use it to find all solutions? Well, so recall, by the theorem, the associated homogeneous equation of star is y double prime minus 2y prime minus 15y equals 0. And if you recall, we found the general solution to this in an earlier example. So by an earlier example, remember we found this c1 e to the 5x plus c2 e to the negative 3x. That has to be what yc is equal to. So put this together. So by the theorem, the general solution to what did we call that? We called it star. The general solution to star is, you just take yc and you add it to yp. So that's going to equal c1 e to the 5x plus c2 e to the negative 3x, and then plus our particular solution, right? Our particular solution is 2 e to the 6x. So this is our general solution. You just add the complementary function to the particular solution. I know there was a lot of information here, but we are going to be expanding on that in the next several sections, okay? We'll be going into all of this in more detail. Thanks very much for watching, everybody.